Okay, so this is our first day of parent functions and transformations. Today is strictly about your old vocabulary and your parent function. So let's look at these. These aren't secrets, right? You know them. This tells you all the details. My goal is to have you be able to think about it and know all the answers without strictly memorizing every detail, right? If you know what it looks like, if you will commit the picture to memory, then you will be able to answer all of these questions if you know what the vocab means, right? So let's think of, actually, I want to think about some words. I'm going to go to this page for a second and go over some of your vocabulary. What does domain mean? Tell me, what's the domain of a function? A domain is all the acceptable x values, right? What would make a number not part of the domain? There's two major cases that make it not part of the domain. And what would those be? Well, it's all real numbers except what? A zero in the bottom. Or if you have an even root, a negative sign. So for example, if I had 3 over x minus 5, right? X can't be 5 because 5 would create a 0 in the bottom. So you always have to watch if you have a fraction with a variable in the bottom, you cannot make that a 0. The other thing is, if this is an even number, like a square root or a fourth root, then we cannot have a negative in there, right? Because right now we're dealing with real number functions. Now, if we get into the imaginary world, we would be okay, but we're not there yet. And how do you write the domain? It is the left number, comma, right number. Like 3 to 7 or something like that. And if it's inclusive, we use a bracket. If it's non-inclusive, we use parentheses. Right? Now, what's the range of a function? All acceptable y values. And we write that bottom, top, right? It must be the bottom first, or it could be a bracket if it's included, right? You have to look at it and tell. And you could have a combination of brackets and parentheses. They don't have to be the same.
So when it comes to the brackets and parentheses, how would you know whether something's inclusive?
Whether it has an arrow for range or whether it's a vertex or something like that. So, for example, if this point was 5, 7, then my range, the bottom would be 7 to infinity, and infinity is a parenthesis. So I actually get to touch that point. If I can't touch it for some reason, if it's open, then I would have a parenthesis. What about concavity? Do y'all know what that means? Now that's a word I can only describe to you visually this year because I need to teach you derivatives before I can give you an algebraic definition. We need some calculus, but we can tell with our eyes. You studied it in physics. What was concavity? Come on, you know. Have any of you ever worn a contact lens? Right? It's shaped round like that. So I'm going to use this curve, right, to describe concavity to you. That's a sine wave. You're very familiar with it. So That was weird. Your definition of concavity this year is kind of be like thinking about a car ride. So if this were a road, right? Let's say that this was a road and you were driving on it. You're out in your car, it's sunny, you're having a nice drive. If you were driving and you got to this point right here and you needed to go on this curve, where would your hands go? Do your hands. Your hands would turn to the right, correct? Well, then in a second, when you get to this point, if you're going to stay on that road, your hands are going to the right, what would happen? Your hands would have to what? Straighten out for a second and then turn the other way, right? That point right here, if you were driving where your hands go back to normal, separates where concavity changes. And that's called a point of inflection. Now we're going to need calculus for me to tell you how to calculate that, but you can see it with your eyes. We won't get in real deep, just identifying it. And then right here, we would say that which one of those do you think is concave up and which one of those do you think is concave down?
I think that the green one is concave down.
Well, let's look. This is pointing which way? Up. So this is concave up, concave down. Down like a frown, up like a cup, if you need to memorize it, okay? So concavity for you is going to be a matter of looking at a curve and seeing that it's curved down or it's curved up, and that division right there where you would have to straighten out the wheel if you were driving is called a point of inflection. Next February, I can go over that with you and we'll do a calculus definition and you'll be able to plug some numbers in. But for this right now, just so you recognize that a curve is concave up or concave down, right? What are end behaviors? Well, end behaviors show us which way the end is going, and we have a specific way we write those, correct? So we have a left side and a right side, right? Correct. Most of the time, as x approaches negative infinity, y goes somewhere. Now, once in a while, and we'll look at it on your curve on the other side, this may not be infinity. If we've got a curve like a square root that starts at 0, we may be approaching 0. But for most of your polynomial functions and curves, we're going to both sides. Now, this could be a different answer. What this is asking is, where does y go? If y goes up, it's infinity. If y goes down, if you got an arrow pointing down, it's going to negative infinity. And we'll look at that some more. You remember the end behaviors, right? You're basically saying on the right side, it goes up or down. And on the left side, it goes up or down. Or it could flatten out to an asymptote. Okay, what about increasing and decreasing? I'm going to use this one to do increasing and decreasing. It helps to have a curve. Right? So now increasing and decreasing is very easy. You just trace your pencil or your finger, and we trace from left to right because that's how we write with a pen, right? So if your pen is moving down, you're decreasing. So what is happening here? Am I increasing or decreasing? Did I go down or up? We went down, so that's decreasing. Then what happens right here? Which way is my pencil going? All right, so this is decreasing, meaning if my pencil goes down to trace the curve, I'm decreasing, and this, of course, would be increasing. I would say this is increasing from 180 degrees to to 360 degrees, right? This is decreasing from 0 to 180. Now, if it's an endpoint or something, we may have a bracket, and we'll get into the brackets in a minute. Okay, and again, this is just vocab, old vocabulary you're bringing in. Do these make sense? Decreasing, increasing, concave up, concave down, concave up. Now, right here, you know that this from 90 degrees to 270, is this one concave up or concave down? From 90 to 270, that would be concave up. Then you'd have a point of inflection, and now it's going to be concave down. All right. What about the vertical line test? What is that? Yes, excellent work. So the vertical line test, we have, let's say, a shape, and we draw vertical lines, right? If it passes the test, function. Let's draw another one. Touches it twice, fail, not function. Everyone's familiar with that, right? If you can draw vertical lines through a graph one time, well, and it only hits the graph in one dot, it's a function. If one line hits the graph twice, you're not a function. If that's the vertical line test, then what do you think the horizontal line test is? It is. So let's draw this again. I'm going to use the same. Only this time we draw horizontal lines. That fails, right? This one passes. What does it mean if you pass or fail? If you fail, you're not one-to-one. And if you pass, you are. One-to-one. Which brings us to the question on your mind now. What does one-to-one mean? One-to-one means the inverse is a function. Okay, so if you do the horizontal line test and you fail, that means whenever you take the inverse will not be a function. That's kind of just vocab right now. That's going to come into play a little later. But for right now, it's kind of making sure you understand a vocabulary word. Plant the seed for later, if you will. We won't do a lot with that right now. Does that make sense? You need a minute to think? Here, let me give you a minute. All right, the next thing is our X and Y intercepts. So what is an X-intercept? Well, X is wherever you cross the X-axis, right? And you can have several of those. And it's written as a number 0, like 50, 40, wherever you cross the X-axis. A Y-intercept is wherever you cross the Y, and that's going to be 0 number, like 03, 02. How many Y-intercepts do you have? Can only have one. Right? Only one Y-intercept. If you have more than one Y-intercept, it's not a function because you're doubled up in that domain. Does that make sense with X and Y intercepts? And when you see that, I'm very picky. In some of the digital programs don't make you write the 0, but for me, if you're handwriting something, X and Y intercepts are, intercept means location, and I want a point. I want 50 or 07 or whatever. I will take points off if you don't write that as a point. Now, some of the math lab software accepts just the number, which drives me crazy, but I want you to build a good habit. Okay, symmetry. Even symmetry means you're symmetric to y-axis, right? So the y-axis cuts your picture in half. Right? Odd is symmetric. Odd means symmetric to the origin. Okay? And if it's odd, it looks the same upside down. Even, of course, the y-axis cuts it in half. That's very easy for you to see. Did the y-axis cut it in half? Now, let's look at an odd function real quick. Now, look at this function, and what happens if we turn it exactly upside down? Does it look exactly the same? It does, doesn't it? Looks exactly the same. So if you're ever in a pinch and you're wondering what happened, is this odd? You're taking a test and you're like, I don't know. Just take your paper, turn it upside down. If it looks exactly the same, it's odd symmetry, right? Even, of course, is very easy to tell because it's cut in half by the y-axis. Okay, so you can tell that symmetry there. Now you're going to see other words, an odd function or an even function. That's not necessarily symmetry. This is talking about symmetry. When you look at some other functions and we want to know if the function itself is even or odd, if the ends go the same way, it's even. If the ends go opposite way, it's an odd function. We'll look at that with our powers in a minute. Continuity, what does that mean? That means, is it a straight line? Is it continuous or does it have holes, right? So that's continuous. And this is not continuous, right? Y'all can visually see that with your eye, right? If it has a hole in it or the lines don't meet up or it's broken, it's not continuous. I think you're good with that. Now, what about max and mins? Local and absolute. Well, let's do our locals. So this would be a local max and a min, right? Now, what about absolute? Okay. Is that the absolute highest point on this graph? There's nothing ever higher, is there? So that's an absolute. This is a local. So that'd be a max, min. Most of the time when we ask for a max or a min, if you don't see anything to clarify, we want any hill or any highest point. Absolute means it's the absolute highest or lowest. Is that good for vocab, or is everybody comfortable with the vocab? It's familiar. You've seen it before. Okay, we're going to go back now and talk about these vocab words with our parent functions, right? Not too much to do. All right, so let's look at these. Linear, formula y equals x. So we need to know that. I can't see it. What do you need to memorize on this? You need to memorize the equation and what it looks like. Because if you know the equation and you know what it looks like, if you understand your vocab, can you answer all of these questions? You can. What's the domain? Well, it goes on forever in the left direction, goes on forever in the right, so it's negative infinity to infinity. What's the range? Goes down forever, goes up forever, so negative infinity to infinity. And behaviors, let's look at this. That says x goes to negative infinity, so that's the left side. This says x goes to infinity, so that's the right side. So on the left side, where does y go, up or down? Which way is this pointing? It's pointing down, so that's negative infinity. This is the right side. Which way is it pointing? It's pointing up, so that's infinity. Negative infinity means down. This means up. Critical points. Those are some important points. Like for this one, I really want you to know the 0, 0. If you know 0, 0, you know the rest because it's a slope of 1. It's up 1 over 1, up 1 over 1. So as long as you know 0, 0, you can graph that, right? And then we've got our absolute value, right? Value starts with a V, and what shape does this have? A V, right? The critical point I would note here would be the 0, 0. Goes to the origin because then it's over 1, up 1. If you know the vertex, then you can figure the rest out, right? And then the quadratic, which is the picture of the curve is called a parabola, right? The function is a quadratic, y equals x squared. Now notice on this one, x squared, square is a 2, that's an even number. This is an even function. With an even function, what do you notice about both ends? They're going the same direction. Let's look at this one. This is x cubed. It's odd, right? It's an odd function. So what do you notice about the ends? They're going opposite directions. So in an even function, now we're not talking symmetry, we're talking function. Even function ends point same direction. Example, both up or both down. For an odd function, ends go in opposite directions. You may not have noticed that back in Algebra 2 when you were trying to learn all of this. It was a lot of stuff, right? So this year we're going to pick up the details that you might have missed. These are all continuous. Yes, they have arrows on both ends. Now we reach our first guy. He's not continuous forever, is he? He starts here and he goes that way. So notice here, instead of saying on the left side, x goes to infinity, we say x goes to 0 because 0 is the most left side, right? So as x goes to 0, y goes to 0 on the right side. So this is left, this is right. As x approaches infinity, y goes to infinity. So notice that slight difference there. Here, x only goes to 0. And we would say this is continuous when x is greater than or equal to 0. Okay, we can't say it's continuous forever because it has a starting point. We could say it's continuous over the domain of x is greater than 0. Or we could say 0 to infinity. But we would have to clarify. We couldn't just say continuous, right? If we want to say something's continuous and it stops, we can specify where it's continuous. Okay, cubic. Notice all of these points have what common point that they all go through so far? These first 6 that we looked at all go through 0, 0, right? That's important because when we do transformations, you may have done transformation tables in the past. Who did those? Did you love them? No, you hated them. If you know this point is here and you know what the curve looks like, we can do all of our transformations with just your eyes. You'll be able to see where something goes and we can take away all that work you do in the transformation table, but it requires you to understand the curve. If you understand it, you can move it away with no trouble. Okay, then we have your exponential and your logarithm. Notice this has a different critical point. The point I want you to know are these points, and we will spend an entire unit on logarithms and exponentials. They have something none of these other functions have had so far. They have an asymptote, right? So this actually never reaches 0. It looks like it reaches 0 because the ink is so thick. But I want you to know an exponential goes through 0, 1. I'm going to call that the pivot point later. And if you have to graph it, instead of getting stressed out, you can just move the pivot point. You basically know what it looks like and you can sketch it very quickly. So you want to know that pivot point. A log has a pivot point where? I want you to notice something. How do you spell log? L-O-G, right? So L-O-G. What does L-O look like? 1, 0. So is it easy to remember that critical point on a log? Look, log, L-O-G, and look where it starts, 1, 0. If you know a log is 1, 0, then you know an exponential is 0, 1. You won't get them mixed up. I was a kid that would run in 0, 1, 1, 0, which one? Then I figured out log looks just like its point. Now I'll never get those mixed up again on a test. Then we have our rational or inverse, if you will. We will always call this rational. You remember it from Algebra 2, we called it radii. We'll spend a whole unit on radii. So this function right here, we spend a whole unit on. This function right here, these functions, we spend a whole unit on. So I want you to just know the basic shape for this one. Now notice this one does not go through 0, 0 either, but we have a point here. 1, 1, and negative. And this has an asymptote down the middle. Now this is 1 over x. This is 1 over x squared. Remember from radii in Algebra 2, if the bottom is squared, it means your ends go the same way, right? Bottom squared is together. Your ends go together. And look what they're doing right here. That's why we have 2 of them. Now, don't panic if you don't remember that. We're going to spend a whole unit on it. But this squared in the bottom is what tells you they're both going the same way. I think that one looks like a volcano. Do you see a volcano? See, we could do lava. Woohoo! Okay, those dotted lines aren't real. Don't draw the dotted lines. That's just what I think it looks like. X squared looks like a volcano. A constant you're familiar with, that's a linear function that's flat, has a slope of 0, right? And it's just y equal to a number. like y equals 3, y equals -2, y equals 7, whatever that is. Goes on and on forever. Notice it's a little different with when you're going, you don't go to, y doesn't go to infinity, y just goes to that number. So when we look at the end behavior, as x goes to the left, y goes to 2. As x goes to the right, y goes to 2, or wherever your location is. The last one I want to mention is a greatest integer function. You may have called that something else. You may have called it a step function. We won't spend a lot of time on this one, but I want you to at least recognize it. Looks like steps. Why do we have this? This is for cases where graphs are not continuous and you're just counting integers. For example, how many people live in your home? 3, 2, 4, 7. Does anyone have 6.5 people? You do not. So certain things you cannot have halves. If you go to the train station, you go to platform 1, you go to platform 2. There's no fractions, they're all integers unless you're Harry Potter. If you're Harry Potter, you go to 9 3/4, but none of us can find that one, right? So these occur when things move up to the next level and there's no in between. Have you ever mailed a letter? You put a stamp on it, right? If you put something, a pack of stickers for your friend in the letter and it gets too heavy, what do? You put a second stamp, but you don't put a half a stamp, right? You have to go to the next stamp. If you're a wrestler, you're in a weight class, right? And if you gain a little bit, you go to the next weight class, right? You can't be in between. Right now, some of you are juniors, some of you are seniors. You're not a junior and a half, right? And get special privileges. You're either a junior or a senior. If you're a junior, you have to go to the junior class meeting. If you're a senior, you go to the senior class. We don't have junior and a half meetings, right? Does that make sense what a step function is for? When we get to those, just so you identify what it looks like, it's got a point there, and what it does is it goes over and makes a circle. So let me enlarge that. What you're seeing with these little things is this. When you get here, you jump up, right? So like when you get here, you have a birthday, now you're 16. You go over here, you live a year, you have a birthday, now you're 17. And that's what this looks like. It's kind of small and hard to see. Okay, notice this, the dots look like a straight line, but they're not connected. It's not continuous. They're going out. Does that make sense as your review of functions? I know these aren't new and I know I went kind of fast. So I'm going to give you a second now. We're going to turn. Let's not look at this page. We're going to look at that in a second. I want you to look at this page and you're going to give yourself a little test. I'm going to give you a couple minutes and you see if you can sketch these. I'm going to pause this recording, so take a second and try. So let me show you how fast I expect you to do this. This is your goal, to go through here and say, okay. Okay, I want you to be that quick. Don't worry about filling these in. Use it. Leave them blank if you didn't get them because you know you don't know those. But your goal is to be able to take a piece of paper and run through those curves that fast. If you can't do it, you don't know them well enough to serve you well for your future class. Does that make sense? I'm not going to give you a time test. This is for you to do at home. Watch something funny. pull out a blank piece of paper and run through your curves, and you should be able to whip through them just like that. Okay, that's your foundation for future math classes. Okay, so we'll back up now. And again, I'm going to give you a little bit of time. I want you to look through here, and you can use your notes, and we're going to do this in class. I am going to come around and check this. If you're at home, you're going to open your screen right dark enough so I can see it. And in a minute, I'm going to go over these with you and check it. But if you're at home, you're going to hold it up to the camera. If you're in the class, I'm going to come around and check it. So this is a grade to do this right now and practice, because that's letting me know if the vocab made sense. Okay, so I'm going to pause this and give you think time, and then we'll come back. Okay, so we're going to check out what you did. Let's see. Okay, so let's take a second. Let's take a second and look at those. And make sure that you got them. If there's anything that you have a question on, please let me know. This is a vocabulary check, right? And if you're at home, when you're done and you can undo your, put your camera on, and you need to hold this page up so you get credit for participating in doing that today. Okay, so I'm going to turn off our recording. This is it. Have a great day.